All right, I hope everyone had a good weekend. We have an exam the next class, right? Next time we meet. And remember, I'm not going to be here. So, oh, there it is. I'm not going to be here, so the proctor will just give the exam, hand it out, and then after you're done, you can leave. All right? And then I won't get those until the grades won't be updated because I won't actually get those exams until next Monday. So I'm thinking you won't have your grades till probably Monday night next week. Just so you know. Now, just about 15 minutes ago, I posted these solutions, like the handwritten solutions, in our Canvas website. Go in there, click on Files, and then inside Files it says like Exam Reviews and Solutions. Click in there, and then it should be there. You should be able to open it and take a look at it. All right? So today, I have a stack of papers going around that should be your 2 quiz grades. If it's a check mark, it's 100. And those grades should be reflected in Canvas. If something is off, just let me know. All right? All right, we will talk more about the exam. I know we talked about it a little bit last time, but we do want to get through a few more things that will appear on the exam. So just keep in mind the review is a guide, right? It's supposed to get you prepared for the exam, but it doesn't necessarily have every single little detail. So pay attention to what we do today, because there may be some questions regarding these topics on Wednesday. So I'm working off page 53 of the packet, and then let me try and open this up. Where's my review packet? All right, we'll see how closely these match up to your questions. Okay, can y'all see that okay? If you have your packet, you should be able to read along with me. So we're going to do some word problems. A lot of today is going to be word problems, all right? It says, first of all, solve the following application problems involving linear functions. So Mr. Thompson is on a diet. He currently weighs 260 pounds. He loses 4 pounds per month. We did a problem kind of like this already. Write a linear model that represents Mr. Thompson's weight after M months. How many months will Mr. Thompson, after how many months will Mr. Thompson reach his goal of 220 pounds? Okay, so let's play that game that we played that one time where I go around and ask questions. I ask you for help. How about we do that? Let's see here. Where did we leave off? Did we go through every group? I feel like we did. Yeah, I got you? I think we did, yeah. I think everyone's gone through. Okay, so let's do it this way then. Let's just start again with this group here, and we'll just kind of go around. So first thing is asked is to write a linear model that represents Mr. Thompson's weight after M months. So what are y'all thinking over there? Welcome back. Sorry. Throw you right into the fire here. Oh, hold on. We're going with this group. You'll get the next one.
This is going to be
You're trying to come up with a linear model, right? Something that represents his weight after a certain number of months. What is that? Say again? Go for it. No one cares. No one cares.
Would it be y equals 260 minus 4 times x?
Okay, so let me just write down what you said. 260 and then minus 4 times x.
Correct.
Okay, so let's take a look at
Or I
this.
guess so.
Okay, so I was going to bring that up, but let's just see what we have here. Y is equal to 260 minus 4x. So let's figure out what each of these pieces are. 260, I'm taking, is the weight that he currently holds, right? And then you're subtracting from it 4 times x, and I think x here represents the number of months, right? And so therefore y would be his weight after so many months, right? Now in the problem it says after m months, right? So if they say in the problem m, we need to use m instead of what?
X and y.
Instead of x. Now with the y, we could still use y, but we need to use m for months. Now is this kind of what you were thinking? Or okay, so let me show you an alternate equation. We could say his weight, right, w, equals 260 minus 4m. Now, again, you could use y, but w makes a little more sense because that's his weight, right? So do we all agree that this is a linear model? I mean, this is definitely a linear model, like y equals and then something with x. These are both raised to the first power. So that's a linear equation in 2 variables. This is also a linear equation in 2 variables, but our variables are w and m instead of y and x. So is that fair? Everyone comfortable getting that? Okay, so have we answered part A? Yes, so we just box this up and move on to the next question. After how many months will Mr. Thompson reach his goal weight of 220 pounds? So we are going to move to the next table. So we're going with the little 2 top over there.
So you just said
Why W to 220 and not M to 220?
because w represents the weight.
Yeah, that's right. So it says, when it says how many months, right? That means that we are trying to solve for M, right? We want to know how many months it's going to take for his weight to be 220. So this is your W, right? So we will replace W with 220. So this is part B, this is part A. So we place W in this equation with 220, and then equals 260 minus 4M. And now we are going to solve this for M, right? So to solve this for M, we need to isolate M. So we'll move the 260 to the other side. If you're looking at the solutions that I put up for the exam review, I don't really show a lot of work. Like on the next step, I would have just wrote like, not negative 60, sorry. I would have wrote what? Negative 40. See, I don't show that work on the review solutions. I'm assuming that you can get from that step to that step. So just subtracting 260 on both sides. And then next step would be to divide both sides by negative 4. So it's going to take him, what? 10 months, all right, for him to reach his goal weight of 220 pounds. Okay. Y'all good with that? All right, let's look at the next one. Whoa. Just messed up. That's the homework. Okay, let's just look at number 2 real quick. A bacteria population doubles every minute. Explain why this is not, this population growth cannot be modeled using a linear equation. We're actually going to talk about this more later in this class. So it's kind of weird that this is appearing now, but let's just make sure we understand this. A bacteria population doubles every minute. Explain why this population growth cannot be modeled using the linear equation. So let me draw a picture. Let's say that we have a bacteria, all right? A very happy that's a little bacteria right there, okay? And it's just one guy right there, all right? And that population, that bacteria will split off and double every single minute, all right? So let's say that this is the bacteria, and then 1 minute later, he's got a buddy, right? There's now 2 of them. And then 1 minute later, how many will there be? There will be 4, because each one of them doubles. And then how many are going to be there after another minute? We're going to have 8. All right, so it's starting to get crowded here. So if I were to try and make a table that shows time and number of bacteria, then at time is 0, that means right when I am about to start, I have 1 bacteria there, right? And then after 1 minute, right, 1 minute, I'm going to have 2 bacteria. After 2 minutes, I'm going to have 4. After 3 minutes, I'm going to have 8. How many would I have after 4 minutes? 16. So what is happening here? What's happening as time increases, each step, what happens to the number of bacteria? It doubles, right? Why can we not use a linear model for this? Why can we not use something that looks like this?
Not constant.
What's not constant?
The bacteria being produced.
This jump is not the same jump every time. So remember how important the slope was? The slope told us rise over run. It said if you move, you have to go up a certain amount, then over, right? Then up and over and up and over. So for every move, let me do it this way. If I have a line like this, then to get to another point, I have to go up a certain amount and over, up a certain amount and over. And so if we move over this amount, this rise will be the same as this little jump. So for every jump to the right, we have to go up by the same amount. That's not what's happening here. See, these are like our jumps. We jump from 0 to 1, so that'd be like from 0 to 1. How much do we go up by? What's our change from here to here? 1, right? So we go over 1, up 1, right? But on the next one, we change from 1 to 2, so we go over 1 again, but how much do we jump by? 2, right? So it'd be like over 1, up 2, and then the next time we move over 1, and then this time we jump up by 4. And so it's impossible to have a linear model for this. Now I know that I would not ask you that on the test, all right? The idea behind that problem is to get us to think that there are some situations, real world situations, like bacteria growth, population growth, that cannot be modeled using linear equations. So we have different types of equations. Anyone know what kind of equation we have to use for this? Quadratic still won't do it. We actually have to use an exponential. It's called an exponential function. But that's later, okay? That's later on. All right, so let's move on. Don't freak out about that question. Let's talk about Kara. Kara? K-Ray? What is her name? Kara? Let's go with Kara. Kara used the linear model y equals 20,000 plus 0.3x to predict her total salary from achieving total sales of x. Interpret the slope and y-intercept in terms of her salary and sales. Okay. So let me write this model down here. If I asked you to graph this, could you? I'm about to sneeze. Excuse me. Thank you. All right. If I asked you to graph this line, could you? Could you do it right now? I hope you could. This would be x, this would be y. Where could I start? What is that? What is this in the problem, and then what is this in the problem? Okay, this one is B. This is your y-intercept, right? And then this one right here is your m, right? And that's your slope. So I could go to 20,000 on the y-axis, which is way up there. So I'm just going to count by 5,000. So this is 5,000, 10, 15. Here's 20,000, okay? And remember, this is her sales, isn't it? That's what it says there. This linear model predicts her total, not sales, sorry, salary. All right, that's her salary. So 20,000, and then this line slopes which way? Does it kind of pitch up? Or does it pitch down? Or is it vertical or horizontal? It goes up. Now, is it really steep? No, it's not, because this is a positive number, right? 0.3? It's positive, which means that it does have a pitch up, but it's pretty small. So a slope of 1 is diagonal, like perfect 45 degrees. That's slope of 1. So 0.3 is going to be less. So we know that this line does something like that, right? And then this right here, X, is her sales. I got those mixed up there for a second. Okay? So it says for us to interpret the slope and y-intercept of her salary. Slope and y-intercept in terms of her salary and sales. So can somebody explain to me what this y-intercept means? Like, what is it? Just tell me about it in words. That's her salary if she had no sales, right? So the y-intercept of 20,000 means so for the y-intercept, let's say, if sales are $0, Kara makes $20,000. Right? That's what that's saying. She goes in, doesn't sell anything, she make 20,000. So we have in some way interpreted what that y-intercept means, right? Now, what about the slope? This is a little weird. Like, how are you going to interpret the slope? Yeah, how do you, yeah, like, what does that 0.3 mean?
That's how much she makes per sale. Extra. Yeah, extra. So she makes one sale, it'll be like that's your 0.3 on top of the 20,000. That's how much she gets paid per sale.
That's how much she gets paid per sale. Now, this doesn't really tell us what she's selling, right? This sales could be like, we could be counting like number of cars she's selling, which I don't think this is the case, because what does 0.3 represent in terms of money? 0.3 is how? It's 30 cents, right? Do you think she makes 30 cents for every car she sells? So if she sells one car, she makes 30 cents? Probably not, right? This is probably, the X is probably like the value of what she's selling. So maybe she sells makeup, okay? And if her sales for the month are $3,000, she's going to make 0.3 times 3,000. So you could then look at it as a percentage, like 30%. So there's not enough information in the word problem for us to truly, accurately interpret what this 0.3 is, other than to say it's something like 30% of her sales, whatever they are, right? Make sense? Okay, so let's just do that. Slope tells us Kara makes 30% of whatever she sells. Point 3, move the decimal 2 places to the right, that's where we're getting the 30%. Okay, there's not one, like, you could have a different answer in words that's still correct. It would just depend on how you communicate it to me. As long as you're not saying something like, you know, she makes $30 for every car she sells. Because, you know what I'm saying? Like, if you interpret it incorrectly, then I can't give you credit. All right, let's move on. I don't like that problem, but all right. tuition. Are y'all getting tired of my stories? I have a story. I'll tell you anyway. Has anyone ever been to a Chinese restaurant down on Broadway called Hung Fung?
Yes.
It's been there for like 1,000 years, I think.
It's like a landmark.
Yeah, and who has been there? Hung Fung? Okay. All right. Well, I'm not going to talk about the food or anything. I remember as a kid, I was probably about 6 years old. I remember going up to the register to pay at the end of the night, and they had this little jar, little plastic jar, and they had Chinese candy. Y'all know what Chinese candy is? It's like dried salted plums. Yeah, okay. So I had this jar full of Chinese candy, and on the little thing in the front, it said, what did it say? It was like what was it? 0.05 cents, like that, right? That's what it said. And I just remember my dad going up there, and he's like, he asked the lady, he said, do you have any more Chinese candy? It was a pretty big bowl, you know, and there's probably 100 pieces in there. He's like, do you have any more? And she's like, oh yeah, we've got, she pulled out this big bag. And he's like, I'll take all of them. And she's like, what? And he pulled out like $2. She's like, what? No, you know, what are you doing? So anyway, this is what? Well, how much is this? This is not quite. This is not 5 cents. This is 0.05 cents. So let me write it this way. If I wrote 1 cent, does everyone agree that's 1 penny, right? But if I wrote 0.5 cents, that's half a cent, isn't it? That's half a cent. And if you write 0.05 cents, then that's 5/100ths. So that's like 1/20th of a cent. So that means 1 penny will get you 20 pieces. Make sense? So $1 would get you what, like 2,000 pieces or something like that? So of course, she's like, oh no, that's 5 cents. And my dad didn't want to argue with her, but he was trying to make a point that they needed to change their sign because it was incorrect. They needed to write 5 cents, right? Now, if you want to use 0.5, then you'd write 0.05, then you would write, dollars or something like that. That's 5 cents. That's 5/100ths of a dollar. Anyways, I don't know what made me think of that. That 0.3, right? You just, like, what does 0.3 mean? 0.05, depends. Is it cents, dollars? She got all mad at him. All right, here we go. The tuition at XYZ, at college XYZ, is $100 per credit hour. Very inexpensive, apparently. And an additional $75 student fee. Okay, so where are we? Right here, this table, these three. Now you can respond if you want. So part A, what is the one-time charge or fixed cost for this?
So it would be the 75 fee.
The 70. So these student fees, right? These have nothing to do with how many hours the student's taking. It's just, are you going to go to college? You're going to pay a fee, right? That fee goes into what, like parking and whatever, other things, right? So if you take one class, you're still paying the $75. If you take 10 classes, you're going to pay the $75. So the fixed cost or one-time charge is $75. Okay, part B, someone else? Same table, someone else?
$100.
$100. Now let's say $100, right? Let's say per hour, okay? Per credit hour is your variable cost. And then we'll move on. Next table. Y'all ready for tuition function? They want it a certain way. They want T of X. This looks a lot like that notation we used before, F of X, but they're using capital T. What do you think they're using that for? Tuition, right? So they're saying, hey, tuition, the tuition someone's going to pay is dependent upon X. So X is going to be the number of hours they take. So what would we write? What do you got for your tuition function? Now it's just you. You're on your own. He just bailed on you.
100.
Okay. Okay, yes, so times the hours, right? Now, because they wrote T of X, they are telling you that it needs to depend on X. So we are going to use X instead of H, okay? But yes, H would have been fine had they not given us this, okay? So I'm going to use X here. So this is $100 per credit hour, and is that it?
Plus 75.
Plus 75. Okay, and now you can see, hopefully you can see, this looks a lot like a linear equation, right? This looks like y equals mx plus b. So b is that fixed cost, the 100 is the slope of the line, and that's all they wanted.
If you were to put that x equals 75 plus 100x, would it still be the same?
What do you think?
I would say yeah.
Yes? Now, why? We talked about this last time. I'm going to see if you can use the word. Because addition is commutative.
Yeah.
Commutative. Not commutative, but commutative. You don't need to know this. I know that you are thinking about it. So addition can switch the order and there's no problems. Can't do it with subtraction, but addition you can. All right, so that's good. Let's look at the next one. Yeah, we see what kind of partner you are.
Me?
Yes, you totally bailed. All right, so the next one, we're going to go straight back. I'll give you some time. I'll read it. Joe has a part-time job caring for and walking dogs. He estimates that his annual insurance, etc., is $420. On average, he spends $4.50 on gasoline per visit. He charges $15 per visit. Note that this is an annual cost function. So there's a lot going on here. It's a lot more complicated than the problem we just did because we have a lot of numbers in here. So the first question is, what is the one-time annual charge or fixed cost? So what do you think back there?
$15.
What? Hold up. What do you got? 420. So what is? Can you describe what that 420 is from the word problem? I mean, I agree it's the fixed cost, but what is it? I mean, it's his what? What is it? It says it right there. Insurance, right? So he's basically got to make sure that, like, if he's walking a dog and he gets run over by a car, he's got insurance that'll cover him when he's sued, right? So that's what that cost is. It's $420 a year to make sure if he messes up, he's protected, right, from lawsuits or something. That's the way I interpret it, right? That's the way you interpret it? So that's a fixed cost. No matter what, if he's going to run his business, he's got to have that insurance, all right? So yes, part A, $420 fixed cost. Is that the only cost that is fixed? In other words, is that the only cost that is not determined by how many jobs he gets? I think so, right? Like the $4.50, that's how much he spends on gas per visit. So if he doesn't visit anyone, doesn't do any jobs, he's not going to pay that, right? The $15 per visit is what he's charging. He's not going to get that money unless he does a job. So everything else depends on how many jobs he does. The only thing that doesn't is the 420. We good? Okay. Part B, I'm going to stay at the same table. We're switching up though. Both of these. Okay, so yes and no. Yes and no. Can you imagine that you are the person who runs this business? Right? So is the 450 coming into you or going out? It's going out. What about the $15? It's coming in. So the variable cost, right? Every time he goes somewhere, he spends about $4.50 on gas out of his pocket, but he gains 15, right? So that variable cost is not those two added together, but what? Subtracted, right? So it's actually going to be the $15 minus the $4.50, which is what? $10.50? Isn't that actually how much he's going to make every job he does? $10.50. He goes and walks a dog, comes back, it's $10, right? So you have to be a little careful with the wording of that. Anyone have questions on that? Okay. And finally, I'll let you two come up with the cost function for us. And we're following this format that when we have a linear equation like this in these word problems, this number is always going to be the fixed cost, and this, or fixed value, and this is always going to be the variable one. That's pretty much the format that we're using for these problems. You have whatever your fixed cost is, the number by itself, and then your variable cost is going to be the number in front of x. So what do you think?
C of X.
Uh-huh.
1050.
Yep.
X
Okay.
plus 420.
Plus 420? What do y'all think? Or is it minus 420?
Minus 420.
Is that 420 money you're making, or it's minus? Yeah, so this is one of those subtle things you have to be careful about because, again, this insurance, you're paying for it, aren't you? So if you go at the beginning of the year, you go pay for your insurance, $420, and you don't walk any dogs, right? 0 jobs, you're in the hole, 420. You've got to do quite a few jobs to break even, don't you? How could you figure out what it would take to break even?
Divide 420 by 1050.
You could replace that with 0, right? Because this is your cost. So you could replace that with 0 and solve for x. That means basically move this over, divide 420 by 1050, and that would be how many jobs you need. They don't ask that, but that's what you would do. Okay. Let's move on. I think that was the only thing they asked on that one. Yep. All right, this one looks very much like one we just did. If college tuition costs $92 per credit hour and fees are fixed at $75, write a formula for the function that calculates the tuition and fees for taking X credits. Write the function. What is the total cost of taking 11 credit hours? So since we've done one just like this, why don't everyone just take like 2 minutes, come up with your function, and see if you can get that last question answered. The total cost of taking 11 credit hours.
Different question, actually.
Pardon? You have a different question? What is yours not tuition?
Yeah, we had different questions on the map.
Totally different?
Yeah, the last
Let me
couple
see.
ones, actually.
Really?
Yeah, this one and yeah, just this one. But that one's different.
Oh, you have meteorology? That's my next question, actually. So let's just do this one. If you don't have it on there, don't worry about it. Just work this one through. Y'all getting that? 1087? $1,087. So if the problems I'm putting up here are a little different than what you have in front of you, then that's probably a good thing. You can go back and work those, and that'll give you some additional practice. Any questions on this one? I called it T of X, but you could have called it anything you want. It doesn't matter as long as you're using X. And the reason you have to use X is because in the problem they say X credits. Otherwise, you could call this, C of X for cost or F of X if you want. No big deal. All right, is this the problem that you have next, meteorology? Is that the same problem?
Yes.
Pretty much, yeah? Okay. All right, so where are we at? Let's go to the back table over there. There's three, there's part A, B, and C, so I'll let each of you pick. One of you gets A, one of you gets B, one of you gets C. So who wants A? You got it? Okay, so A is asking, according to the slope, what happens as the altitude increases?
Well, H is in thousands, that has to be clarified first.
Uh-huh, H is in thousands. So H represents your what?
Feet.
Feet, so that's your height, right? Okay, so it's asking what happens as the altitude increases. Let me ask you this. What thing, this equation up here is connecting what two quantities together? Temperature and height, right? Or you could say altitude and temperature, right? If I asked you to graph this, and this is your height, which is your altitude, and this would be your temperature, right? Because the left side is temperature. This would be a line according to this model, right? And which way would this line pitch? It would be down, right? So whatever it is, it would look like that, right? So now, if you look at part A and it says what happens as your altitude increases, then your temperature drops. So as your height gets bigger, your temperature goes down, right? And that's the way it works, generally speaking, right? You start going up a mountain, it's going to get colder. So you can answer this question by just looking at the slope. Because the slope was negative, you know that as the altitude, as the altitude increased, as the height increased, your temperature would be going down. Does that make sense, everyone? Okay, so part A, you would need to say temperature decreases. All right, good. Who's getting part B? Part B is tricky. Tell me what you're going to do for part B.
You're going to substitute the 12,000 feet for H.
Okay, so everyone agree that we're going to replace this H with this exactly 12,000. Are we going to plug 12,000 in? We have to be really careful here. H is in thousands of feet, okay? See how it says that right there? H is in thousands of feet. So if it was 1,000 feet, you would plug in 1. If it was 2,000 feet, you'd plug in 2. 3,000, 3, and so on and so forth. So you're actually, for part B, you're going to be taking that function and you will be plugging 12 into it, not 12,000. And that's because of the wording of the problem. So do y'all see how you have to be a little careful with that? And let's see, negative 3.5 times 12 plus 58.6. Who has that for me?
16.6.
16.6? What did you get when you plugged in 12,000?
12,000?
Yeah, did you try that and plug it in? You hadn't done it? Had anyone done 12,000? No?
You're going to get like
You'll get like a huge negative number.
1,000 or I don't know.
Yeah,
something
which means, anyone up there is like rock solid ice cube, right? All right. Part C. So who's up?
I just plugged in 32
Okay, for like the y value. So it's actually, on this equation, you replace this side right here, right, with 32 degrees. That's right. Because this time they give you the temperature, right, and they're asking what height. So you're trying to solve for h. Here's your equation. You're going to try and solve for this h, so you've got to replace this side of the equation with the temperature, which is 32 degrees. And had you finished solving that yet?
7.6.
Okay, so let me put this in here. So you move things around. You got 7.6. Anyone else get 7.6? Yes? Okay, so is this correct? Have we answered the question?
No.
Almost, right? It's saying at what height? So are you saying at 7.6 feet? No. We're saying 7,600 feet, because remember, this is in thousands. So we need to convert this and write 7,600 feet. What they were trying to get us to do is try and figure out at what point, at what altitude would we be at like the freezing point, 32 degrees. That's terrible. This is really a bad picture. That's a bridge. Sorry. It's bad. That's a bridge. Okay, have you ever noticed that when you drive over a bridge, they usually have like some sort of a gap over here in the road and some sort of gap. Sometimes it looks like little teeth that come together like this. Have y'all ever noticed that? Okay, well, they're there. Do y'all have any idea what these are? What that is? Why there's a gap?
The locks.
What's that?
The locks.
The locks?
Like a little, they're like pieces they put together.
Okay, but they leave a space. Why do they leave space in between the road, you know? So it can expand. So here's the deal. This part of the road is touching the ground, and this part of the road is touching the ground, and this part is not. So they always say like bridges freeze first, right? That's because, you know, the earth is warm, and so the earth is in contact with the road, so this road surface is warmer than this road surface because there's air under it, right? So when things heat up, they expand. And I mean, just a little bit, you can't tell, but when you heat something up, it expands, and when you cool it down, it contracts. So they have to put little spacers there. That way, when the bridge expands and contracts, it doesn't crumple itself, right? Make sense? And I'm telling you this for a reason. I just said that when you heat things up, they expand, and when you cool them down, they contract. Most things do that. There's one thing that doesn't do that. And because of this one thing that doesn't do it, we actually are here. We're alive, like we exist. You all know what I'm talking about? Water. Water is one of the only substances that when you heat it up, it does the opposite. And when you cool it, it does the opposite. So if you've ever had if you've ever put a glass bottle into a freezer, like to cool it off and then forgot about it, you go back, most likely the glass bottle is shattered. And that's because when water freezes, it expands. It's supposed to be the other way. When you heat it, it's supposed to expand. But water, when it freezes, it expands. And that's also why ice cubes float. When you freeze ice, it expands so it's less dense, so it floats up to the top as opposed to the bottom. Most things, when they're solid, they would sink to the bottom. Now, why does that mean we're alive? Okay, so here's the earth, and here's a pond, okay? And here's some little fish. You've seen my fish before, right? Okay, so there we go, right? You have a pond. In other words, you have life inside of this pond, all right? When it gets very cold, what happens to a pond? I mean, really cold, like below freezing, what happens? It freezes up on top, doesn't it? Now, if you were to drill through the ice, it would still be water below it, right? The reason why that happens is because when water freezes, it's less dense, so it floats up to the top. So the top surface will always freeze over first. But once it freezes, now what it does is it acts like a blanket, and it keeps the heat from the earth here, and it doesn't let it escape. So this stays water underneath, all right? If it was the other way around, if water did not have that property where it would freeze and expand, if it were to freeze and contract, then the ice would start to form on the bottom. And then what would happen is the heat could continue to escape because there's no blanket, so it would just get thicker and thicker and thicker, and everything would freeze all the way through, all the way to the top. You wouldn't have that blanket effect. And so everything in there would die. So because of that weird property, it's kind of assured life can exist. It's kind of weird that it works that way, but it does. What made me think of that? Oh, I was just looking at freezing temperature, sorry. My brain is always all over the place, sorry. Hope it's not too annoying. All right. Trust me, if you were in like my calculus class, I wouldn't have time for random useless information, okay? But this class is kind of fun because we can just talk about whatever, whenever, except politics. Politics or religion, yeah. We'll stay away from those. All right, here we go. This table's up. I'll let you read it. We haven't done one like this. Do you have any idea how we could approach this?
No.
No?
Is it the 143 times 365?
Are you getting 365 for a year?
Yeah, or no?
I think what they're trying to get you, what they're giving you here are two pieces of data. They're telling you what happens in 1990, and they're telling you what's happening in 2000, right? And they're trying to get you to predict if it still is behaving this way, what's happening now, right? Do you all see that from the question? Do you read it that way? 1990, Americans ate out 143 times a year. 2000, 170 times per year, if the growth is constant. So if it's maintaining that same trend, then what would be happening now? So let's draw a little chart of what's happening. Let's say this is the year, and this is the number of times Americans ate per year. So if I go here to 1990, what did it say the number was? 143. So I'll just put right here like 143, and I would put a dot. Does that make sense that that first piece of data tells me that? And then, what, 8 years later? So 1991, 92, 93, 94, 8 years later, whatever, in 2000, it's 170. Okay? Yes?
If we just wanted to find the constant rate of what it increased each year, we would just subtract the two numbers and divide by 10, since that's the age of the
Exactly. That's exactly what we're going to do. But what I want to do is see if you can see that this is exactly something we've already done. And it has to do with the fact that we have 2 points, right? We have 2 points on a line right now, don't we? Don't we have 2 points on a line? And what we're trying to do is we're trying to figure out what's happening over here in 2018, right? That's the question. Like, what is this point right here? How high is it? We're assuming that we have the same growth. So what we need to do is, why don't we come up with an equation for that line? Can we come up with an actual equation for that line? We have 2 points, don't we? We have this point, which is 1990, 143, and we have this point, which is 2000 and 170. So for that line, can you give me the slope of the line? And you're going to do that calculation exactly right now, aren't you? What is the slope of this line? Rise over run, right? y2 minus y1 over x2 minus x1. Does this look familiar now? So that's your 170 minus 143 over 2,000 minus 1990. So I'm looking at this as being my x1, y1. This is my x2, y2. And then I'm using this formula to get the slope.
So
27 over 10, which is 2.7. All right? So that's my slope. That's the slope of that line. That does not tell me what's happening in 2018, does it? But I can now use this formula. You did this as a quiz at the end of class last time, didn't you? Use that formula to get your actual equation of your line. We know the slope now, don't we? 2.7? And do we have one of the points? Do we have x1 and y1? Yes. So I'm going to just replace. This is y minus 143 equals 2.7, then x minus 1990. Okay, this is not the answer, but this is the equation. This is probably one of the most realistic problems we've actually done up to this point. Because what we're doing is we're doing modeling. We're looking at some things that have happened, and we're saying, hey, if this trend continues, can we predict what will happen later? And so we take the 2 points, we create a linear equation, and now we can use that linear equation to do anything we want. With me? So how do we answer the final thing? If the growth is constant, how many meals do you expect us to eat out this year? So what are you going to do? Here's your equation, right? Replace what? Do what? I didn't hear you.
You would again, 28.
For what? 2018 for X or for Y? Don't say anything. I'm going to force you. Are you guessing?
Yeah.
Okay, look at your graph, okay? Your x-axis was your year, right? Your y-axis was how many times we're going to eat out, right? So your x-axis, you're going to replace the x with the 2018. So it's not a coin flip. It's right there. I know you can do it. So everyone good? So all I'm going to do now is I'm going to replace 2018 right in here and then solve for y, which will be the number of times we ate out. Okay, here we go. Y minus 143, just rewriting this, equals 2.7 times 2018 minus 1990. And I'm solving for y. So I'm just going to do this subtraction. Is that 28?
Yes.
Do what's in parentheses first, and then do the multiplication.
75.6.
Is that the final?
No,
No? Okay. All right, so y minus 143. You said 75.6? And then finally,
218.
add it up, or add 143, so 218.6. So make sure you understand that. That is saying that if we were to believe that this trend is continuing to occur, that is, as the years go by, Americans are eating out more frequently, then we should expect, using those two data points from 1990 and 2000, that in 2018, families are eating out 218 times a year. I don't know about that. Why is this linear model not a good model?
Because it doesn't say per day or per meal. Like, and you have the typical person has like 3 meals per
Yeah,
day.
that's true. You could be talking about breakfast, lunch, and dinner here. But even if they were talking about breakfast, lunch, and dinner, what do you think is wrong with us continuing to use a linear model? Let me go back to our picture. Yeah, so let's say this is a year, and this is number of meals again, right? If we used a linear model, then are we eventually going to get to like some ridiculous number that wouldn't even be reasonable, like there's 365 days in a year, right? Let's say you ate all 3 meals out at a restaurant every day. That's like what, 1,000 or so? You know, a little over 1,000 meals is the most you could possibly do, right? Like, but because this is linear, it just continues to go up and up and up, right? So eventually, like, here's 1,000. Eventually, you get to like 2,000, right? In some year, I don't know where, but we get to 2,000. It wouldn't make sense, would it? So although the linear model is decent for looking at maybe years near 1990 and 2000, it wouldn't be a good model long term. We would need a better model, and it couldn't be a line. It'd have to be something else, probably something that looked like this. Like here's 1,000. Like 1,000 would probably be like a ceiling that we would never see ourselves going over. So our model might be something more like this that has a curve to it, right? Something like that. And this is again going to be like an exponential or what we call logarithmic functions do this sort of thing. So I'm just trying to point out that linear equations are good, but they're not enough. We need other types of functions in the real world in order to make the real world actually make sense and do good predictions. All right, let's continue. How are we doing on time? We've already done an hour of this. Mixtures. All right, we have not done a mixture problem, and I asked you on your review to omit that. Remember that one problem I said don't worry about it? I think it was the last one. Okay, but we're talking about it now today. So mixture problems cause students issues. I've always, in my history of teaching, students have always had trouble with mixture problems. Let's see, we'll do our best. If there is a mixture of 7 liters, that's the amount that we have there, 7 liters of water and 17 milliliters of ink, write in decimal form how many total liters there are of this mixture. All right? So this is just the first mixture problem, so we're not doing anything super complicated yet. We've got 7 liters of water sitting in some jug, 7 liters. And then in that, right, we're adding to that also 17 milliliters, right? That's our ink. And this is our water, H2O. And they want to know in decimal form how many total liters there are. So what am I going to need to do? I got to change milliliters to liters first. So this is one of our conversions, and you would look off that chart or you get onto Google or whatever and search it. So how do we change 17 milliliters to liters? I'm going to move that decimal point. Which way? To the left, how many times? How many? So you go to your table, there's a chart there. And if you're moving from milliliters to liters, what page is that on? What page is that on?
27.
27. So if you look on page 27, you'll see milliliters, and then you have to move 3 places to the left to get to liters. So we're going to move this decimal point 1, 2, 3, put the decimal point here, which means there's one more 0 in there, isn't there? So this 17 milliliters is actually just 0.017 liters. And now that they're the same unit, right, liter and liter, we add them together. So how many liters do we have? 7.017 liters. Questions? Convert milliliters to liters, then add together. That was really just a conversion problem. That's all.